This lecture, we're going to begin a topic called arrow pushing. This is something very near and dear to my heart, and is really, while it starts out as much like many of the things we've talked about, like Newman projections, Fisher projections, chair structures, while it starts out feeling a little bit unusual, it proves itself to be a very valuable model for understanding organic chemistry. If you understand arrow pushing, you can really understand thousands of types of chemical reactions and chemical processes without memorizing them. So this is kind of the framework that arrow pushing allows us to take advantage of. And again, it's incredible how powerful it continues to be. And so it's really important for us to kind of get going with it. But once again, hang with me if this feels awkward at first. It's just, gosh, this is just so critically important. But anyway, okay, so we have the notes in front of us. This is Introduction to Arrow Pushing. So in what this is a method to broadly understand transformations or reactions of organic molecules. Okay, so in reality, if we think about chemical reactions, which is what I'm really excited to talk about, and hopefully you're really excited to learn about. I mean, chemical reactions are the transformation of matter. This is why I do what I do. I want to make interesting things and do interesting reactions to get there along the way. But chemical reactions, these things that I just really hyped up quite a bit, chemical reactions are simply kind of processes that involve just making and breaking bonds. And these bonds that I'm speaking about, for us, they are covalent. Okay, so covalent bonds involve the sharing of electrons. So we have shared electrons. And rearranging the electrons will determine how reactions actually occur. If covalent bonds, the things that get made, or get broken as a result of a chemical reaction that we're trying to understand, if for us they involve shared electrons, it's the rearranging of these shared electrons that determine how reactions will proceed or how reactions will occur. What's going to happen? Okay, when we take a chemical reaction, when we're saying that we're doing a chemical reaction, what happens and why it happens is governed by why electrons rearrange the way they do. And so what we're going to do is use a technique to understand why electrons are going to do the things that they do. And it's really important to capture that. It's really important to realize that it's the electrons, not the protons and the neutrons. Now, the protons and the neutrons greatly, significantly influence where the electrons are going to go. In fact, they dictate it. They are the ones kind of telling the electrons where to go, but it's where those electrons actually go and what they actually do and how they actually move that determines what happens in a chemical reaction. So what I want to do is show an example of a reaction, and not just any reaction, one of the most important reactions. So So an example of a reaction could just be an acid-base reaction, one of the most fundamental reactions in all of chemistry. Now, if we take the classic Bronsted reaction, what we do is we take a hydrogen cation. It might be tied up with water, but let's just assume that it's by itself. Hydrogen cation, and this is just a proton. Right, if you do the electron configuration of H+, you see that it has 0 electrons. And if you look at the atomic structure, you see it has 1 proton and 0 neutrons. So 1 proton, 0 neutrons, 0 electrons. We may just as well call this hydrogen cation a proton. Now, a proton is also an acid, as we'll see, because an acid can react with a base like hydroxide. And we can show how these react using the reaction arrow formalism, where we just have some arrow showing the progression from, of course that's an arrow, shows the progression from starting materials to products. So I have my reaction arrow showing that H+ and OH-, so this is now an oxygen anion, in this case, an ion that has a negative charge. And this is, excuse me, bummer, I ran out of space. This is our base. Okay, now these two things are going to react to form water. And this is just the definition of a Bronsted base. If you've taken general or high school chemistry, there are a few definitions for what constitutes an ester base. This is the most common one, where you take two things, react them together, and make water and possibly some salt. So let's take a step back. This is a reaction. We started with two things, a hydrogen cation and what's called a hydroxide anion. We let them react with each other to change the form of matter, so that instead of having these two charged species, we had a neutral water molecule. So I said, let's take a step back. And what we want to do is ask, what are the charges on H+ and OH-? Okay, these species are charged. What do those charges, correspond to? Those are just our formal charges, which we have an equation for. Formal charges are equal to the group number minus the number of bonds minus the number of unshared electrons. Okay, so we talked about that before. We have the number of bonds, we have the and the number of electrons. We add those together, and the number of electrons that are just the total number that are unshared. So a lone pair counts as a number 2 in this case. Okay, and then the group number is just that column number on the periodic table. So if we look at this and we have H+ reacting with OH-, and I put the minus over the oxygen, and that is an anion called hydroxide, and we let those proceed to give rise to two products. Where do these charges come from? Well, on H+, we have a group number equal to 1. The bonds are equal to the electron count, which is equal to 0. So 1 minus 0 minus 0 is equal to 0 plus 1, a plus 1 charge. And that's where this positive comes from. And again, chemists for some reason don't like to draw the number 1, so it's just a plus sign. Now for the minus sign on hydroxide, we actually have two elements to consider. We've got O with 3 lone pairs of electrons and a covalent bond, Sorry about that. Parenting, you know. Okay, so we have an oxygen with 6 dots around it and a line to a hydrogen atom. Now that oxygen has a group number of 6. It has 1 bond, and it has the number of unshared electrons is equal to 2, 4, 6 for having 3 lone pairs. So 6 minus 1 minus 6 is equal to a -1. So that -1 corresponds to the negative charge on our hydroxide, and the +1 corresponds to the plus sign on our H+. Okay, so those are just formal charges. If we looked at the other H, we would see that we now have a bond, so it's 1 minus 1 equals 0. Now, this +1 and this -1, let's not ignore them. They're the ones that really dictate what's happening in this acid-base reaction. That is to say that electrostatic interactions dominate the types of, or I guess dominate the outcome. Let's go back to dictate. I don't like dominates. Sorry. Dictate the outcome of chemical reactions. Okay, that is to say that opposites attract, and it's opposite charges that attract, and like charges repel. Okay. So in this case, we have a plus on the H and a minus on the oxygen. So those two things attract one another. There's an attractive interaction, an attractive electrostatic interaction between the hydrogen and the oxygen. And so they're going to come together. So when they come together, the product is formed. By combining opposite charges, covalent bonds form and products arise. Okay, so let's think about this. As the charges attract atoms together, what we're going to see is that bonds will start to form. And if bonds are made, okay, if bonds are made, that's a really important step in a lot of chemical reactions, the formation of bonds. We can also talk about bond breaking, but we'll probably save that for next time. But what I'm saying is that it's like the H plus and the OH minus see each other, and the negative charge and the positive charge attract to one another. Now, the negative charge is, in this case, localized on the oxygen atom, and we saw that from the formal charge calculation. It's fixed at that oxygen position. So when the two things attract, it's not just any old part of the molecule. It's not the other hydrogen. It's the oxygen with its negative charge that's attracted to the positive. So it's like the negative charge comes over and sort of attacks the oxygen and, the hydrogen. And what we get is we basically steal 2 electrons that were once lone pairs, and we form a new bond. Now, why can we do that? Well, if we look at the oxygen atom now, the formal charge on that oxygen is, what is it? Well, it's still group 6. Now it has 2 bonds. And now it no longer has 6 unshared electrons. 2 of the original 6 are now shared. So instead it has 4 unshared electrons. 6 minus 2 minus 4 is equal to 0. So the charges were attracted. We formed a new covalent bond. using the unshared electrons from the original oxygen atom. We neutralize the charge, we make a covalent bond, our product is formed. So what is actually happening during the course of the reaction? Well, anytime we form a covalent bond, the same type of thing happens. That is, orbital overlap enables the sharing of electrons. That is to say, we've got a hydrogen. Charges aside, charges are important because, well, let's go ahead. Let's draw the charges. We have a plus charge here, suggesting that that hydrogen is going to be attracted to the oxygen with its negative charge. Now, the oxygen, we can just draw the covalent bond to the other hydrogen as a line, but if we're going to show orbital overlap, let's consider our hybrid orbitals. This is an sp3 orbital with a lone pair. So we have an sp3 orbital with 2 dots for the 2 electrons. And then what we're going to do is let those 2 engage each other to form a molecular orbital when we see overlap of the oxygen atom. Now it's no longer negatively charged because the electrons that were once a lone pair are now shared between the hydrogen and the oxygen. Now this is the same as drawing a line between the hydrogen and the oxygen. Because we have the electrons being shared using a now molecular orbital that resulted from the overlap of 2 atomic orbitals, one of which was hybridized. Now that we have a molecular orbital, the electrons simultaneously exist over the hydrogen and the oxygen, which is by definition a covalent bond. The electrons are shared across the bond. Okay, so that's the molecular orbital notation. This is showing how bonds are formed using molecular orbitals. Now, in my opinion, it's a bit cumbersome to draw out the orbitals, show them overlap, indicate where the electrons are, and then just continue to suggest that we have this overlap and a covalent bond has been formed. Instead, an alternative way of depicting a bond is to bond formation and bond breaking is to use curly arrow notation. So an alternative approach is the curly arrow notation. It's a bit awkward, but what we do is we actually show bonds being made or broken by showing an arrow indicating the path of electrons. So if I have my 2 reactants, what I'm saying is that the negative charge is going to have an arrow coming from it to the positive charge. We go negative to positive. It's a bit backwards from the dipole arrows, but this is the thing we have to get used to, and this is the thing we need to get used to sooner rather than later. Is in the curly arrow notation, we start from negative and we go to positive. The reason being is this curly arrow is to show the path of the electrons. It's the path of the electrons, and specifically, it's the lone pair that makes a bond. So it's the lone pair of electrons that actually goes out and makes the bond to the other hydrogen atom to give rise to water. Now, did the electrons actually move through the curly path as I had drawn? That is, do they start and they go north a little bit and duck down south? No, that's just for aesthetics, okay? I don't know why we don't just draw straight arrows. Maybe it's because straight arrows would get complicated with our reaction arrows that showcase the chemical equation. But this is what we do. We like to show it as though the oxygen is kind of moving towards the hydrogen. If you had drawn this, that's okay. If you had drawn this, that's okay. If you had drawn, let's get ridiculous here, just to emphasize, as long as we're going from negative to positive, it's okay. Like if you're like, well, I'm going to go over here, go over here. I would prefer you not do this. But I suppose it's okay. I mean, we're trying to just, as long as you have an arrowhead at one end, and it's that end that's pointing towards the positive, then it's okay. What if I flip the arrows around? Willoughby, it seems like we've got a lot of wiggle room. What if I have the arrows going from the positive to the negative? No, no, no. We're pushing electrons. Positive charges are the absence of electrons. Delta positively charges indicate a deficiency of electrons. We're trying to show the movement of electrons. So our arrow starts where the electrons start, and they end up where the electrons end up. So this one gets a big no. It's negative to positive. I know it's opposite of dipole arrows. I get it. Okay. But that's what we're trying to show is the pathway that electrons take. They're showing how these things are colliding. The oxygen is attracted to the hydrogen because the oxygen has something, and it's that something that leads the oxygen and the hydrogen together. So we want to show the movement of things, electrons, not the movement of holes, which are positive charges or delta plus. So it's always minus to plus, and it could go any direction as long as it's minus to plus. Okay, these are all okay. Smiley face. But frowny face, anytime we have a plus sign going to a negative sign. That's not going to happen because that's the movement of nothing to something. And we can't move nothing, right? We can't move these electron holes, okay? We move the electrons. That is to say, there's no electrons to, and everybody likes this, attack. I'm fine with it because things got to collide. It's not because I'm a violent person. Atoms got to collide to make bonds. That's how we get orbital overlap. That's how we share electrons. But it's the electrons that do the attacking, and it's the electrons that are then shared in the overlap. We don't share the cation. Okay. So that is sort of an introduction to the curly arrow notation. Basically, we're showing movements from places where there are electrons to places where there are not electrons. We could have other examples where we could have lone pairs from neutral molecules can move, but we have to maintain overall charge. We have to maintain overall charge. You'll see what I mean in just a second. Okay. So if we had, well, let's go back to our original. What does this maintain overall charge? Well, if I have H plus and OH minus, and I show the negative charge engaging the H plus to form this molecule, on the right side, we're neutral. Did I maintain charge? I did, as long as we're focused on overall charge. Okay, I realized that the charge on the positive cation went down to 0. That is, the charge on the H plus went down to 0, and the charge on the O minus went up to 0. But overall, we have +1 and -1 on the atoms. We are overall neutral. So when you're pushing arrows to show what types of products are being formed, the overall charge needs to balance on the left side and the right side of the equation. So for example, maybe you don't want to show OH minus interacting with H plus, and instead you want to have it reacting with a strong acid that you can actually put your hands on. Well, in that case, we'd have the negative charge add to the H of hydrochloric acid. What's cool about this, and what's cool about the curly arrow notation, and don't worry, you won't get it this lecture. You need to watch the next lecture. But we can actually show bond breaking and bond making events happening in this at the same time. So OH minus, this time drawn on the left, is going to attack H, why H? Because it has a delta plus when it's attracted to the negative delta minus or the more electronegative chlorine atom. But now the H, as the OH minus is coming in, the H is now overwhelmed with electrons. It's exceeding its octet, which is just 2, right? Hydrogen only wants 2 electrons to get to its octet. So what we can do is we can show the curly arrow notation to have electrons moving from a position where they're shared to a position where they're unshared. That is to say, this bond is going to break to give rise to this molecule plus Cl. Now the Cl has an extra lone pair of electrons. These used to be in the bond. And now that Cl has a -1 charge because the formal charge on chlorine, well, chlorine is a group 7 element minus 0 bonds minus 8 electrons is equal to -1. Okay, so we use the curly arrow notation to show the breaking of bonds along with the making of bonds. In that last example, we looked at what we had was a case where we made bonds and broke bonds. If that doesn't make sense, I get it. That was early. So what we're trying to do is build our way up to using curly arrow notation. And this is a 2-semester objective. We're not just going to get there right away. If you want a great book to learn this very efficiently, there's a book called Organic Chemistry 1 as a Second Language, first semester topics, not second semester, first semester topics. It does an excellent job of teaching electron pushing. And I try to take a lot of their approaches in the problem sets, but it's just something you kind of work your way into with some practice. And we're going to continue to practice in upcoming videos.